Hi everyone. Today I want to tell you about the modes of the 2D wave equation on a circular membrane. So we're going to go through the process of separation of variables and see how we can compute the modes of the wave equation, but now when we're trying to model the vibrations of a circular membrane instead of a rectangular one, like in the last video. So here I have a picture of our circular membrane. You should think of it as a drum attached to this circular frame. And we want to understand how, if you hit the drum, for example, how would it vibrate, right? I'm going to give a name to the radius of this circle. So let me call it the radius R. And let me give a name to the disc filling the frame. I'll call it dr. Right, so we're going to model this vibration by a function u defined on the real numbers across the disk to the real numbers. It's a function u t x y whose graph, the graph of u, models the position of the membrane. Right, just like before, once you fix the time t, then this function as a function of xy will model the vibration of the membrane. And we know that this function is going to have to solve a 2D wave equation. So u t xy must be a solution of the wave equation which is partial t squared of u is equal to c squared Laplacian of u, and we're gonna assume that the membrane is fixed at the frame, so this function is equal to 0 for all time and for xy in the boundary. Alright, so the question we want to analyze is, what are the modes of this problem? Once we can compute the modes, right, so the standing waves of the drum, we could add them up together to create more complicated vibrations and, for example, solve initial value problems. So the way we're going to solve this problem, because the boundary condition is given on this circle instead, it would be very hard to apply separation of variables to the variables x and y. Basically because it would be very hard to impose the boundary conditions after you separate the variables. So what we have to do in this problem is we have to use polar coordinates. So we use polar coordinates. So we write xy as r cosine theta, r sine theta. And so our function u t xy we can write as u t r cosine r sine. And this is kind of bad manners, but we're just going to denote this u t r theta. It's bad manners because really I should give this a different name, maybe call it u tilde or something. But we're just going to call it u, and we're going to say it's u but with the coordinates r theta instead of xy. So this lets us separating variables in this way now will be a lot better. The trade-off is that the Laplacian in these coordinates is a lot more complicated, unfortunately. Well, not a lot more, but a little bit more. So as we already discussed in class, you can use the chain rule. Right, so for example, what we have to do is, so the Laplacian of u, this is the second derivative in x of u plus the second derivative in y of u. But we want to turn this into an operator that only takes derivatives in r and theta. Right. So what does it look like in terms of r theta? And what you have to do here is use the chain rule. So for example, we know that we can write the partial derivative of u with respect to x using the chain rule as the partial derivative of u with respect to r times the partial of r with respect to x plus the partial derivative of u with respect to theta times the partial derivative of theta with respect to x. A similar thing holds for y, partial u, partial y. It's partial u, partial r, partial y, plus partial u, partial theta, times partial theta, partial y. And so as long as you can write r in terms of x and y, you can compute these numbers here. So you can compute this, and this. As long as you can write r in terms of x and y, which you can, right? So you can write r, it's actually equal to x squared plus y squared square root. So you can compute these numbers here. Theta is more complicated. You can write theta, for example, as tangent inverse of y over x. But you could use, so this will not be defined when x is equal to 0, for example. But in fact, for you to take a tangent inverse, you also need to assume that the y variable is positive to use the normal definition of tangent inverse. In any case, we're not going to dwell very much on this issue. You use the chain rule and you plug these things into the expression for the Laplacian, and you find, okay, what you find here is that in polar coordinates, the Laplacian looks like Laplacian of u is equal to second derivative in r of u plus first derivative in r divided by r plus second derivative in theta divided by r squared. Okay, you get a new page. And so this is very important. Once we change variables, the form of the Laplacian changes. It is very tempting to say, well, the Laplacian is the second derivative in x plus the second derivative in y. So in polar coordinates, it would be second derivative in r plus second derivative in theta. But that is not true, unfortunately. And so you need to use the chain rule to kind of see how this operator looks like in these new coordinates, and we can find this expression here. Okay, with this expression, we can just go ahead and start our separation of variables method and compute the modes of this equation. Okay, so computing the modes. Alright, so we're going to start by assuming that utr theta can be written as a function of time times a function of space, which is going to be in terms of polar coordinates, right? Plugging this into the wave equation, like, so the left hand side is the second derivative in time, which will take two derivatives of g dot dot t f r theta, and on the right hand side, wait, did I write the c squared? I did. Okay, so it's c squared times the Laplacian, which I'm just gonna keep it like that. The Laplacian only involves derivatives in r and theta, as you can see here. It doesn't involve any derivative in time, of course. So it doesn't take any derivatives of g. What you see on the other side is c squared g of t times the Laplacian of f. Okay, so we can, as always, divide by c squared g of t f r theta on both sides. And we obtain that g dot dot of t divided by c squared g of t is equal to Laplacian of f r theta divided by f. The left hand side only depends on time, which does not show up on the right side. This means that this quotient here has to be equal to some constant, right? Right, this is a function of time that doesn't depend on what the value of time is, so it has to be a constant function. And once we do that, then we get two differential equations, one for f by looking at this equation, and one for g by looking at this equation. And so we get that for g, we get the g dot dot of t is equal to k c squared g of t. For f, we get the Laplacian of f r theta is equal to k f of r theta. Alright, so we have these two equations. And what we have to do now is we must focus on figuring out what f has to be. As you can see, f has to be an eigenfunction of the Laplacian operator. But we first focus on what f has to be because the boundary conditions of the problem is really going to restrict the values of k, the possible values of k that's going to generate non-trivial solutions, right? So you could solve for g now, but we don't know what k really looks like yet, so it's good to leave that for the end. Right? So we first focus on f, so we compute f r theta by paying attention to the boundary conditions, considering the boundary conditions. Okay, so what are the boundary conditions? So as in the beginning of the problem, we really only put one boundary condition, that u t x y is equal to 0 for xy in the boundary of the disk. In polar coordinates, this means that u t capital R theta, where this capital R here is the radius of the disk, right? This means that that has to be equal to 0 for all t and theta. Because being on the boundary is the same as your radius being equal to the radius of the whole disk. Right? Using our formula, this means that g of t times f of r theta is equal to 0 for all t and theta in r. And if we assume that the solution is non-trivial, we know that there should be some value of time for which g of t is not 0, and in that case we would be able to divide by g of t, right? Which means that so for non-trivial solutions, there is a time, say t star, sometime such that g of t star is not 0, which means this has to be true for all values of t and theta. In particular, we can take t equals to t star f r theta. So this has to be true now for all values of theta. We fixed t equal t star. And we know that this g of t star is not 0, so we can divide by this on both sides, and we get that f, oops, I'm sorry. This was supposed to be capital R. So fr theta is equal to 0 for all theta. Alright, so that's the boundary condition for f. Ooh, I guess I need a new page. So the problem that we have now is that the Laplacian of f is equal to k times f r theta, and f of r theta is equal to 0 for all theta. And there's one more thing that we should write here, which is that this function f in fr theta is actually periodic in the theta variable. So let's see why. It's basically because of how we define the function utr theta. So you see, utr theta was defined to be utr cosine theta r sine theta. So if you add 2 pi to theta, right? So if you consider utr theta plus 2 pi, you add 2 pi to the cosine and the sine in here, and cosine and sine are periodic with period 2 pi, so that doesn't alter these coordinates xy, right? Basically, a given point xy, you can choose many different angles for it, right? The angle with the x-axis. I should have drawn a picture here. The polar coordinates to remind you. But if you have a point here, this length is the y variable, right? And this length here is the x variable, the x coordinate of the point. For the polar coordinates, we're using these coordinates r, which is the distance to the origin of that point, and this angle with the x-axis, which is theta, right? But you could choose many angles because you can add a full lap and you represent the same point. Okay? This makes it so that this function utr theta is periodic in the theta variable. Right? So, and I'm going to impose that. That's also sort of a boundary condition. This is a boundary condition for the r variable, and this is a boundary condition for the theta variable. Fr theta is periodic in theta. With period 2 pi. Okay, so now this is the problem that we need to focus on. So to solve this problem, this is a partial differential equation. We use separation of variables. Okay, so let me again write down the formula for the Laplacian because we're going to need it. The Laplacian of f is second derivative in r plus first derivative in r divided by r plus second derivative in theta divided by r squared. Alright, so let's use separation of variables. Variables. Which means that we're going to consider f r theta of the form a function just of the variable r times a function just of the variable theta, right? So the product of two functions of just one variable. So now the equation looks like okay, that got a little weird. The equation looks like, so here you have Laplacian of f. Here's the form of f. So let's go one by one. First is the second derivative in r. It's only going to take derivatives of p, right? So p prime prime of r times q of theta plus first derivative in r divided by r. So we're going to take only a derivative of p, first derivative of p, don't take derivatives of q, divide by r, plus second derivative in theta now, divided by r squared. A second derivative in theta will take two derivatives of the q function. So p of r, q prime prime of theta, divided by r squared. That has to be equal to k times f, which is p times q. Okay, so now that's what the wave equation looks like. And what we have to do is separate variables, right? So we want only r's on one side and only thetas on the other. Okay, so the first thing you could do now is divide by p times q. On both sides. So this gets rid of this q there, so you get p prime prime r. This also gets rid of that q plus p prime. Okay, so that divides by p. P prime of r divided by r p. Plus here the p is going to cancel, so you're going to get q prime prime theta divided by r squared q of theta, and that will be equal to k, just some constant. So now we're almost happy with the situation. The thetas and the r's are pretty separate, but you still have this r squared here, which is easy to get rid of. You just multiply by r squared on both sides. So we're going to get r squared p prime prime of r over p plus, now the r squared cancels one of the r's there, or that one r. We get r p prime over p. Multiplying by r squared here will just leave us with q prime prime over q. And don't forget the right side, k turns into k r squared. Right? And now I'll send the theta to the right side and take this r and send it to the left side. It's going to look like this, and I'm going to put everything under p on the left. It will look like r squared p prime prime of r plus r p prime r minus k r squared p all over p. And on the right side, I get minus q prime prime of theta over q. And again, the left side is only a variable of only a function of r, right? But it's equal to this thing on the right side, which does not depend on r. So this is a function of r that does not depend on what the variable r is. So it's a constant function, so it has to be equal to some constant. I'm going to call it L because it doesn't have to be the same constant as k. So you need a new number. Sorry, a new letter. It's a new constant, so use a new letter. Alright, and we can again match the two equations to get what is the equation that Q has to satisfy and what is the equation that P has to satisfy. Alright, so Q, we get the Q prime prime of theta is equal to minus LQ of theta. And for P, we get the R squared P prime prime plus R P prime minus K R squared P is equal to LP of R. Yeah. So that's the equation for P, which we're going to rewrite a little bit here. I'll just send this to the left. It's going to look like R squared P prime prime plus R P prime minus K R squared plus L P R equals to 0. Alright, and here I'm going to kind of go a little bit fast through the boundary conditions. Again, because for non-trivial solutions you can rewrite, let's go all the way up. Here are the boundary conditions for F. Yeah? And this will create boundary conditions for P and for Q. So you're going to say like, oh, FR theta equals to 0 for all values of theta, but for a non-trivial solution, there must be some theta value, you can call it theta star, such that Q theta star is non-zero, and you'd be able to divide by Q to say that this equation implies that P of capital R is 0. Right? It's similar to what we did before. So I'll just do that quickly to say that here the boundary condition for P is that P of R must be equal to 0. And the boundary conditions for Q is that Q is a periodic function. Q theta is periodic because F was periodic in the theta variable. Period 2 pi. Alright, so we have that problem for Q. And there's one more small detail here that's going to pop up. You can think of it as a boundary condition that this function P of R is finite. I'll say it like that, finite at R equals 0. So we will see that when we solve this differential equation here, there are going to be basically two solutions for it, like A times one solution plus B times the other one. One of the solutions is going to go to infinity as R goes to 0, which is not going to be good for us, right? Because this would mean that our membrane is kind of like going to infinity. The vibration is, the amplitude is going to infinity at the origin. That's R equals 0 is the origin of the disk, right? Which is not good. So I'm going to add that as a boundary condition, although it might be a little bit more subtle than that. But, right, we just need to solve these two problems. The problem for Q we have already solved in a video actually. So this we're trying to find, this is an eigenfunction of the second derivative operator. You can see it through that perspective. And we have computed those. It has to be an eigenfunction, and it has to be periodic of period 2 pi. What we find is that such eigenfunctions will look like, so first L, maybe I'll write this in the next page. So for Q, we have Q prime prime theta is equal to minus L Q of theta Q theta. I'm going to write it like this, 2 pi periodic. So we already solved this problem. We know that L must be equal to n squared for some integer n. So integers greater or equal to 0. Okay, so this is important. We figure out the constant L. And the function q, once you fix the integer, qn theta has to be some multiple of a cosine n theta plus sine n theta. Now, these constants c and n, they're kind of going to be superfluous. Okay, so instead of saying that we found like a, you can think of it as a two-dimensional family of solutions because it can choose any value for the numbers c and d, these two constants. I'm just going to write it like this for every integer. So first, when n is equal to 0, this sine solution doesn't exist, right? So let me parse a little bit. This thing is what I'm trying to say. For n equals 0, the only solution you find is q0. Oops, that turned into a theta. q0 of theta, cosine of 0 is just 1. Okay, it's the constant function. And for n greater than 0, then you kind of find two functions, two different modes. And I'm going to denote it by qn, and maybe I'll write it, how should I write it? I'll write plus and minus, but it doesn't really matter. Qn plus will be the cosine, and qn minus is going to be the sine, right? Why is cosine plus and sine minus? There's no reason. Maybe instead of plus and minus, I don't know if this is going to be confusing, but instead of plus and minus, I'll put, what about C for cosine and S for sine? Is that okay? Hopefully. Okay, so we only find this cosine mode and the sine mode. I just want to take the values 1, 0, and 0, 1, right? That's what I'm doing here. All right. So we found what the function q has to be. I just wrote it like this so that I could get rid of the c's and d's, right? All right. Now let's focus on the function p, right? So the function p, I'll write it here, it has to satisfy r squared p prime prime plus r p prime minus k r squared plus l p is equal to 0. P of r is 0 and p finite at r equals 0. How do we solve this equation? So to solve this equation, we need to kind of do a change of variables. Okay, so so first what we can do is we already figure out what L has to be. So let's plug it in there, right? So L is equal to n squared. So I should say here n. So L equals n squared, already fixed. So we already chose that integer n. And then this turns into the equation r squared p prime prime plus r p prime minus k r squared plus L PR equals 0. And one thing that I'm not going to explain, because it really would take, I mean, this is not such a simple equation. You need to solve it using a power series method. But we can reduce it to a PIZZELL equation. So I'm going to tell you one thing already, is that this constant k for positive values, or when k is equal to 0, there are only trivial solutions satisfying our boundary conditions here. Okay, so I'm not going to really explain why this is true, but it is. And basically, at least for example, when k is positive, you can change variables here, and what you end up with is what is called a modified PIZZELL equation. But the solutions of that equation either don't have a 0 and are not able to satisfy P of R is equal to 0. So they actually never vanish, so they don't have zeros, and this can't be satisfied. And even those, like, I think none of them have zeros, or there's one that maybe has, oh, and you could try to create a 0, but then you would lose this finiteness at R equals 0. But in any case, like, I don't want to dwell on that. So for positive values of k, there are only trivial solutions, and we want non-trivial, of course, non-trivial solutions. So let's focus on what happens in the case where k is negative. So if k is negative, then let's call k equals to minus a number h squared, okay, because it's a negative number, so we can write it like that. And then we're going to change variables. Right. So we're going to call s, the variable s, is equal to h times r. So first, let's see. This equation looks like r squared. Now it looks like r squared p prime prime r plus r p prime r minus, okay, so k now is negative h squared. So minus negative h squared r squared is going to look like plus, you're going to see h squared r squared minus l p prime r. Okay, so it looks like this now that we evaluated what h looks like now, right? All right, so the variable, we're going to introduce this variable s equals to h times r. Notice then that we can say that ds is equal to h dr. Right? And we're going to introduce a function w of s. The function w is just the function p, but with a change of variables. Is p of s over h. Okay, which s over h, that's r. Right? It's just p of r. Right. So hopefully this is not too confusing. But what is the purpose of doing this? So what is the first derivative of this function w? Right. So let me box our change of variables here. Okay, so the purpose of doing this is that, for example, the second derivative, or let's do the first derivative first. The first derivative of s, this is of w, dw ds, right? That's what it is. You can use the chain rule. This is dw dr times dr ds, if you use the chain rule. And then how to compute the derivative of w with respect to r, you look at this formula here. W of s is the same as the function p of r, right? So if you take the derivative in terms of r of w, what you get is p prime of r. And what is dr ds? You can look here, dr, you divide by ds, that's 1 over h. Okay, and what you find is that p prime of r is equal to h w prime of s. And you can do this again to find out that, you just do exactly the same thing to find out that if you take 2 derivatives of r, that's h squared 2 derivatives of w. Okay. And if we use that, oh, I apologize. You probably already were losing your mind here. This p should not have a derivative. Second derivative, first derivative, and no derivatives. Alright, sorry for that. But if you use now this substitution, p prime prime of r, put in h squared w prime prime, and the p prime of r, put in h w prime, we get the following equation for w. And so r squared h squared w prime prime of s plus r h w prime of s plus h squared s squared. Oh, and I also forgot to do the n squared here, huh? So this L was n squared. I'm sorry, there's a lot going on, so I start losing track of. L equals n squared, so I should have written it here. Alright, I'm really sorry. I hope it wasn't too confusing. But L is equal to n squared, so this L turns into n squared. The n squared now is here. Alright, so, oh, and that wasn't an S. Losing my mind. H squared R squared minus n squared. And P of R is the same as W of S, so I'm going to write W of S. And now I just want to turn these R's into S's, but R squared H squared, that's S squared, right, from our definition of S. So we get S squared W prime prime S plus S W prime of S plus S squared minus N squared W of S is equal to 0. This is the PIZZELL equation. Right, so if you just do that change of variables, the equation that we have for P, the only problem is that the PIZZELL equation here, if S is your variable, here you should have S squared. But on our equation for P, R was our variable, but then we had this number multiplying R. You just need to do this change of variable to get rid of it. And you arrive in the PIZZELL equation. The solutions look like, for each choice, so N is chosen here. The solutions are, let me not write that in blue. Solutions are W, I'm going to write Wn S, it's going to be a constant times Jn of S plus another constant times Yn of S. So these are just functions. This is the PIZZELL function of the first kind. And this is the PIZZELL function of the second kind. Alright, so we're not going to go through the derivation of how to compute the solutions of this equation. Again, you do this by applying the power series method, the so-called Frobenius method. And it's a little bit tricky. It's kind of like when we derived the solutions of the Legendre equation. it takes quite a bit of work to write like a power series expansion for j and for y. But you can do it, and you find these two solutions. One is odd, the other is even. So you find these two solutions. And this means that P, so this is W, right? So P of R, by definition, is W of S, which is A Jn of S plus B Yn of S. But then you can write S in terms of R, right? S is just HR. So this is A Jn HR plus B Yn HR. That's what P looks like. But then the boundary conditions force some things. Boundary conditions. My computer glitched for a second there. Boundary conditions. So first, we have this condition that P of R is finite at R equals 0. Right? We cannot have, and by this I mean that P cannot go to infinity when R approaches 0. And this forces the constant B to be 0. Okay? Because, so what I would recommend is you look up, because I don't want to do that in the middle of the video, but you can look up PIZZELL functions on Wikipedia, and you can look at the graph of these PIZZELL functions of the second kind. Okay, it's supposed to be a capital Y, so I'm going to put a little bar right there. But these functions over here, the PIZZELL functions of the second kind, they go to infinity at R equals 0. They kind of look like this. Something like that. They go to, or a negative infinity or something. It depends on whether B is positive or negative. Some condition there. Right. But if we want our function P to be finite at R equals 0, we need to get rid of this second function of the second kind. It's going to give us trouble. Right? So this is, so at this point, we find that P of R then has to be a multiple of a PIZZELL function. You can just take the multiple to be 1. Taking A equal to 1. That's okay. In the end, we're going to get constants from G. So when doing P and Q, you don't need these constants. They are superfluous. Okay, but the other boundary condition is that P of R is 0. Which means now that P is equal to this, that Jn of HR has to be equal to 0. Which means that H times R needs to be a 0 of the nth PIZZELL function. We're going to denote that by beta nm. And this notation stands for the mth positive 0 of Jnx. So what happens here, I'm going to draw a picture there. A PIZZELL function of the first kind usually kind of looks like this. Most of them look like this. It's kind of like a sine or something, and then they keep oscillating forever, but they kind of taper down. But so say that this is the graph of J3 of x, okay? Let me write it like that. So this right here is the first 0 that is positive. So for n positive, so J0 doesn't vanish at 0. But all the other jn's for positive n, they're going to have a 0 as 0 right here, and you don't want to count that because it's going to make h equals 0. It's going to destroy everything. So you don't want to count that one. So this is the first positive 0. That's what we're going to call beta 3, 1. Right? It's the first 0 of J3x. I'm just explaining what the notation means with the two numbers here. Right? So this is the second 0 of J3. So that's the number that we would denote by beta 3, 2. Okay? This one is the this is the third 0, beta 3, 3, third 0 of the third Bessel function. This is the fourth, beta 3, 4. Okay? So the first index says what is the Bessel function that you're looking at. The second index says which 0 are you looking at, right? But because Jn of HR is equal to 0, it must mean that HR is one of these zeros. Does that make sense? And so from here, we can solve for what the constant h has to be. H has to be equal to beta n m divided by r. Okay, and this is for m, some integer, which is positive. It starts at 1. All right, and so this determines a few things. It determines the formula for p. So p n m of r. Right, so we chose the number n and the number m to figure out which of the zeros the h was related to. This is equal to the Jn function times, so here's the formula for p. P of r is JHR. So h is beta n m r over capital R. Okay, so this is what p is. And we also had the formula for k, right? K was minus h squared. So we find that then k is equal to minus beta nm squared over r squared. Yeah, so these, remember I said computing f will restrict the values of k that will give us non-trivial solutions, and this is the restriction, right? K must be one of these numbers for us to get non-trivial solutions. Alright, so what we found is that for n m integers, n is greater or equal to 0 and m is positive. If you want to solve Laplacian f r theta is equal to k f r theta, with f r theta equals 0 for all theta, and f r theta periodic in theta with period 2 pi, the solutions look like, so it's going to be the p times the q. The p is the Bessel function, and the q, remember, was either a sine or a cosine. Here's the q. And the n equals 0 is a little bit different than the n positive, because the n positive you get a cosine and a sine. Okay, so let's write it down here. So for n equals 0, it was going to look a little bit different. N equals 0, you're going to get p, so let's see, f of 0 m r theta is p times q, which is going to be j0, that's the n, of beta 0 m r over over r times q, but the q0 was just 1, so it doesn't show up. And for n positive, then we get f n m. And then you need to decide if you're going to use the cosine or the sine. Right? So there's the sine one. It's jn beta n m r over r times sine theta. And you have f with the cosine. Right, so p times q, p times q. Right, so those are the f's that we find, and we also find that the number k is minus beta n m squared over r squared. New box. This tells us what f is, and it tells us what k has to be for us to get non-trivial f's. So these are the solutions of this problem here, right? So you want eigenfunctions of the Laplacian. We need f to vanish at r. That's why we need to rescale this Bessel function here. And we want f to be periodic in theta, and that's what gives us these sines and cosines. Let me box the case separately as well. Okay, so we found the f's. We're only left with g's now, right? We need to compute the function g, and then we'll be done computing the modes. But this is really the harder part. Right? So we computed all the solutions of f. Maybe I'll recap before I go to g, or maybe I'll recap after I find g. I'll recap now, right? So let me go back up. We did a lot of math. Okay, so we did the separation of variables, right? We wrote u as g times f way in the beginning. We found these two equations, one for f and one for g, and we say we'll do g last. So now we're at the time where we're going to do g. But we already solved the problem for f, right? So we compute f by considering the boundary conditions. We found this problem here. F has to be, solve this equation here, being an eigenfunction of the Laplacian. It has to vanish at the boundary and has to be periodic in theta. We use separation of variables for f to find p, make it p of r times q of theta. Did the separation of variables, and we found these two problems, right? One differential equation for q and the variable theta, one differential equation for p and the variable r. The differential equation for q wasn't too bad, although it did take us a whole video to solve, but we already had solved it. This has non-trivial solutions when L is equal to n squared for some integer, not negative n squared because there was already a negative sign here. Yeah, so L has to be equal to n squared. And Q has to be a combination of sines and cosines. And to kind of get rid of these constants C and D, we wrote it separately like this, right? So for n equals 0, you only get the constant solution. And for n positive, you get these two solutions, either a cosine or a sine. I decided to put an upper script here. C when I'm using cosine, S when I'm using sine. Those are the Q functions. The P functions are solutions of this differential equation with this boundary condition. We first noticed that we already figured out what L is. L has to be equal to n squared. So we plug it into our equation here. And now I told you that this will not have any non-trivial solutions for positive values of k. Now you just have to trust me on that one. But if k is negative, then we wrote k as negative h squared, right? You can do that because it's negative. And we change variables. We use this h here that showed up to change variables, right? S the new variable, is h times r. So if you want, what is this number h? It's just the value of k. You take k, it's like square root of negative k, right? That's what h is. All right, but we use it to change variables. We define this function w of the variable s. It's the same as p of r, right? And we find that w, because p satisfies this equation, w has to satisfy this equation here, which is the PIZZELL equation. And so the w function has to have the form aj plus by, where j is a PIZZELL function of the first kind and y is a PIZZELL function of the second kind, which means that p has to have that form, but with hr, because that's what s is. The condition of being finite at r equals 0 discards the y function, because PIZZELL functions of the second kind go to infinity when r goes to 0. So p will have to be just j times hr, right? So a PIZZELL function of the first kind, and the fact that it has to vanish at capital R forces this number h to have this form, where beta is one of the zeros of the nth PIZZELL function j and x, right? Right, so we found q and we found p, and so f is p times q. So for choices of integers n greater or equal to 0 and m strictly greater than 0, the n is choosing the n for the q function, and the m is choosing basically the 0 of the PIZZELL function, right? The function f, I separated because the q's were separated, right? I separated when n is equal to 0. F is p times q. Q is just 1, so I didn't write it. And p is just this, a PIZZELL function of n equals 0. And when n is positive, you get an f with a sine or an f with a cosine, right? So a PIZZELL function times a sine, that's the q, or a PIZZELL function times a cosine, that's the q. So j is the p, and sine and cosine is the q. And because k was negative h squared, this is what k has to be. All right. So this is what f looks like. Finally, we can compute g. So finally, oops, didn't realize I was in purple. Finally, we compute g of t. So g had to satisfy this pretty simple differential equation, k c squared g of t. But now that we fixed the value n and m, and then we fixed the constant k, right, we get the following equation. I'm going to write g and m dot t, and I'll substitute what k has to be. It's negative beta and m squared c squared over r squared times g and m t. All right. This is a harmonic oscillator equation, and g and m t is combinations of sines and cosines, right? And this number here will influence the frequency of the harmonic oscillator, right? This is related basically to the square of the frequency. So it's going to be a n m. So for the g, you can leave the constants here. A n m cosine. Do I write sine first or cosine first? No, I don't remember. Cosine beta n m c over r t plus b and m sine of beta and m c t over r. Okay, and it's good to introduce a name for this scaling that you have to do inside of the cosine. So we're gonna denote that by lambda. That's what we usually call lambda. So lambda and m is beta n m times c divided by r. Okay. But, you know, we have G and we have F. So what are the modes? The modes of the wave equation on a circular membrane are let's write the n equals 0 case separately. N equals 0. So here, maybe I'll say for n m integers, I should probably start the sentence with that, right? But let me write it at the end here. For n m integers with n greater or equal to 0 and m strictly greater than 0, you get a mode u0 m t r theta. I'm gonna write it. Okay, so it's gonna look like a 0m cosine beta 0m c t over r. Am I able to do that? Plus, I don't know if it's gonna fit, b 0m sine of beta 0m c t over r. That's the G. I'm gonna have to scooch. Just the G is pretty long, right? And then the P is just J0 M. Oh, sorry, J0 of beta 0 M R over R. And the Q function is just 1 for n equals 0. Right? So let me center this expression a little bit. Okay. For n greater than 0, then we get a sine mode and a cosine mode. Right? So u n m t r theta. The G is the same. A n m cosine beta n m c t over r plus b n m sine beta n m c t over r times the p function, which is j n beta n m r over capital R. Okay, so there's one with cosine. Oh man, I don't want to write all of this. So this is the cosine mode, and there's a sine mode. TR theta. I wish I could copy and paste, but I don't think I can. Copy. Oh, I can do that. This is great. Can't believe it. Alright. So this is sine. It's exactly the same thing, but the Q is a sine. And those are the modes. The modes of the wave equation. You choose two integers, n and m. N is choosing the frequency of the Q function. So the frequency of these cosines. And m is choosing the 0 of the PIZZELL function that you're going to need. and you get these modes: G times P times Q, G times P times Q, G times P, and Q is 1 in this one. And lastly, just to finish this, these are waves in the drum, right? So they're going to make a sound, and the pitch of the sound is the frequency of the vibration with time, right? So the vibration with time is all about the function G here, and the frequency here is going to be, let me call this number lambda, right? So the period is going to be 2 pi over lambda. The frequency is 1 over that, so it's lambda over 2 pi. So the pitch of the U and M mode, and here you could put sine or cosine, is lambda n m over 2 pi, which you can write, we have a formula for lambda, is beta n m c over 2 pi r. So this is the frequency of the sounds that this drum will make, right? So it's kind of interesting because the frequency of the sounds is related to these zeros of the PIZZELL functions. So drums produce very interesting sounds. Alright, so I think this is the end of the video. We computed all of the modes of the wave equation in the circular membrane. You could use these modes to solve an initial value problem. I attached an extra credit problem in the last worksheet for you to do that if you want some extra points. But I just want to understand the structure of, want you to understand the structure of the modes, right? So this, it's very similar to the rectangular problem that we solved, right? You get the sines and cosines, and then in the rectangular problem you would get a cosine times a cosine or something like that. But in this case, when you separate the variables for f, you get this PIZZELL function showing up because of the change of variables that we had to do. And so the shape of the membrane really affects what the modes look like. And yeah, all right, so see you guys in class.